Right, hello and welcome. This is a physics video and a physics video to be precise. Now what I'm going to try and cover in this video is I'm going to cover pretty much everything of simple harmonic motion. Partially because I don't think as a topic it is that varied, and it's just something we can cover, I think personally, in one video, sort of easy, nice to summarise, if that makes sense. Okay, so let's kick off. So, when we talk about simple harmonic motion, generally what, if you're just using this as a recap video, what you generally might find is simple harmonic motion in the exam is generally referred to as a pendulum. And it's something, pendulum that's going backwards and forwards, oscillating at a maximum displacement, etc. It goes backwards and forwards. And we get a bit more into the maths of that a bit later on, but essentially that's the kind of situation we are dealing with when we talk about simple harmonic motion. Now, for something to be simple harmonic motion, it's not actually simple, even though that's what irritates me about this topic. It's like, oh, it's simple harmonic motion. It's simple. What are you, thick? It's not simple, so don't get put off by that. Either that or I am actually thick. But seeing as you're listening to my YouTube video, I don't think that'd be such a good thing for me to go out and shout about, would it? Okay, let me just change the lighting in here. So not only a physicist, but also photography person. Anyway, so let's kick off. So there's two factors you need to know about. Now I'm going to leave them at the top of the board through the duration of this video, so you can constantly remind yourself of what two things that make something a simple harmonic motion. Now, generally in the exam, you won't be asked to say, is this a simple harmonic motion or is this not a simple harmonic motion? Generally what they'll ask you in the exam is, you'll say, tell us two things that an object or a mass or something must have in order to be defined as being in simple harmonic motion. So, in shorthand, what's that saying is, what are two things that make it simple harmonic motion? So, the first thing is the acceleration is proportional, so there's a little fish symbol, to the displacement. And now you could go and say this displacement from the equilibrium, but I'm just going to put displacement because I'm quite lazy. The other factor again is to do with acceleration, and it says the acceleration is always, you can underline always if you want to, but obviously you wouldn't do that in the exam, always in the opposite direction to motion. Okay, so they're the two factors really. So just the acceleration is proportional to the displacement, and the acceleration is always in the opposite direction to the to the direction of motion. So just so you can just give you copy that down if you want going to. So I can have a drink. That's a cup of tea that. Because obviously I made it. Anyway, so let's continue with this. So we've got our first theory out of the way. We've sort of defined what simple harmonic motion is, and I've said them two things that are behind me. Okay, so for the rest of this video, I've got a little agenda here. I'm going to explain something called free oscillations. Again, there's two factors to them. And then I'm going to go back to it's not so much simple harmonic motion, it sort of is, but it's going to relate back to our Unit 2 physics of, if you remember, Hooke's law of T equals K times delta L. And then I'm going to be explaining something called damping, which just changes the oscillations of simple harmonic motion, so I've already told you a bit there. And then I'm going to be going on something related to free oscillations. It's called forced oscillations and resonance, if that makes, I can't even say anymore. And then after that I'll just be going some basic, well not basic, again this is basic in the same sense that this is simple, and I'll just be going through some formulas that you get given in the exam. The reason I'm not going through them at the start is purely because I don't want to confuse you, because there's no I'm not going to explain these rules. Purely they won't ask you to prove these rules in the exam. You will just be asked to use them. That's generally the way with physics. Hence why I'm leaving them to last and just going to fill you in the end. Okay, so the first thing I said we were going to do is something called free oscillations. Now, free oscillations are not oscillations that just occur for nothing. Obviously, this is physics. We wouldn't just imply that. Okay, so free oscillations. These are oscillations which have a constant amplitude and have no outside forces acting on them. So that's what a free oscillation is. So there are two things. So they have a constant amplitude and have no outside forces acting on them. What we mean by outside forces is if the pendulum is swinging, I don't just put my hand across and swing that ball left and right. Yeah. So I'm doing it anyway. So, sort of related to what we said about simple harmonic motions, there's two things to remember. So, we said the acceleration was proportional to the displacement, and acceleration is always in the opposite direction to the displacement. So that was simple harmonic motion principles. And then we talked about free oscillations. We said they are oscillations which are of a constant amplitude. So when we say amplitude, obviously I'm going to rub this off if this works. So that is a wave, hopefully, of constant amplitude, which means the troughs and the peaks of the wave occur at exactly the same point. So basically, if you've got a, if we relate this to our swinging pendulum, then the maximum displacement, basically from the equilibrium position, if we call a little dot here E, it's going to have the same distance. So basically, D is going to be the same on each side. So the radius is going to be the same on each side, essentially. So that's what we mean by constant amplitude. So that's it in terms of the sine wave, which we can actually relate to this idea of simple harmonic motion. So there, I'll just again move out of the way so we can have another drink because my throat's killing me. I'll also, obviously the real reason is so you can copy the diagrams down if you want to. And basically, as I said, we're just, them two diagrams there are just examples of constant amplitude, which just leads to the two factors of, if you want to call it that, of free oscillations, which are they have a constant amplitude and there's no outside forces acted in them. So as we said, what we mean by no outside forces is I'm not pushing on the ball. I think it was a pendulum. Now, I was going to leave this till later, but I think it's quite a good time now to go on to something called resonance and forced. Actually, no. So hopefully you copied them diagrams down, and the reason I said that was because I wanted a drink and obviously tea, not alcohol. That'll come later on in life. When I'm still creating these YouTube videos, so don't worry, get to uni and I'll still be doing these. So a lot more joy to come. So they're free oscillations, and then what we said we're going to go on to now is I'm going to go on to something called resonance and what's it called? Resonance and forced oscillations. Oh my god. Forced oscillations. Now the reason I've done this here, I was going to leave it to last, but because I'm a crazy guy and I can change my mind, I think it'd be a good idea now to explain why this is related to free oscillations, and so how the idea of simple harmonic motion, all of these ideas that we've been going through are related to simple harmonic motion, and I'm not just plucking them out of thin air saying, oh, this is related to this, because you have no idea of that. So just to reiterate, simple harmonic motion, we said the acceleration was proportional to the displacement. That's one factor of it. Another factor of simple harmonic motion is the acceleration is always in the opposite of the direction of motion. You don't need to know the ins and outs of the mathematics of that. Obviously you need to know the mathematics of the acceleration of simple harmonic motion, but that's something we'll go on to in a later, I was going to say tutorial, just in a later, whenever I've got some spare time. And then we said free oscillations was oscillations of constant amplitude and no outside forces acting on them. Now you should already be starting to tell from the word forced oscillations, it's going to have some external input on it. So let's start with that, because I think that's the most relevant to what we've just been doing. So forced oscillations, it's actually the opposite of pre-oscillations, apart from the amplitude I'm assuming stays the same. So basically I'm assuming, because you don't need to specify that. Forced oscillations are where the frequency of the object, so the frequency, again if we go back to our idea of the pendulum, so the frequency of the pendulum, obviously I'm just using of the pendulum as a background sort of theorem, so you can be able to work it out in your head. So the frequency of the pendulum depends on the frequency of the applied force. So basically what this means, so let me write this down, of the applied force. So what this means is the frequency, if I'm pushing along this pendulum and I'm the only thing pushing along it, the frequency, I can change this frequency of this pendulum to whatever I want. So if I want it to be really a low frequency, I can just push it in a slow direction, in a slow frequency. But if I want to up the frequency, I can up the frequency by pushing it more. Hopefully that makes some kind of sense. Now resonance, that's not so related. That's why originally I thought I'll leave this to later on. Because it does introduce a new concept really. This forced oscillations is sort of quite similar to free oscillations in terms of the no outside forces acting on them, so I'll just put a little thing there. What we mean by resonance, it's a fancy word for saying this occurs when the frequency of a system, so I just put when the frequency of a system, because I actually don't want to be intelligent. Oh good, sorry. Get some exercise doing this, tell you. Frequency of the system is equal to the natural frequency this system. Now you might be going, Will, what do you mean by natural frequency? Well, natural frequency just means the frequency is sort of related to this free oscillations. So this is basically where the frequency in which there are no outside forces acting on the object. So it's quite close to free oscillations. The frequency when there is no outside forces. So basically the main difference between free oscillation and natural frequency is natural frequency occurs when there are no outside forces acting on the object, and it doesn't specify about the constant amplitude. You don't need to specify that. So that's the main difference there. It's just physicists trying to add something else, like it just said try to want to. Okay, so that's resonance and forced oscillations, and you can see there how it's related to free oscillations in terms of constant amplitude and no outside forces. So the forced oscillations related to free oscillations because it said there was no outside forces. Sorry, there was outside. So resonance and forced oscillations are the opposite of each other. So the forced oscillations, where there is an outside force, and that directly affects the frequency of whatever you're acting on. And then resonance is the opposite of that. So when there's no outside forces and the frequency is equal to the natural frequency of the object, and we said the natural frequency occurs when there's no outside forces. So you can see how they're all intertwined. Okay, so that's quite a few key bits there. So I'll just need to recheck my schedule a second. So if you want to just note down that, and I'm just going to take a second now just to check my schedule, where we are with the schedule, and what I need to get through. Right, okay, so just be a minute. You copy that down. Alright, okay. Alright, so work that out. Now, I did want to leave that to last because it was quite a little bit, it's sort of a little bit confusing, that, to be honest. But hopefully you saw why we affected that there. Right, so I'm going to rub that all out. I'm going to leave the two factors of simple harmonic motion at the top because I think they're the most important. The rest of that was just a load of, probably seemed like a load of gobbledygook to you and me. Now, what I'm going to start here is, it's going off really Unit 2 physics, applying our uses of force equals mass times acceleration, and using the acceleration formula that you are given. I'm not saying you know because I haven't gone through it yet. That you're given in the formula sheet for A2 physics. Now, what is the acceleration formula? The acceleration formula is minus 2. One sec. I tried to do that off the top of my head there. 2 pi frequency squared times x. X being the displacement. So that's the acceleration. Now the reason I put that out is we're just going to be using the derivative of force equals mass times acceleration, which equals mass times gravity, as acceleration is the acceleration due to gravity. Assuming no outside force are acting on this object. Okay, so how can we apply, so this one up here is sort of the main one really, in terms of the acceleration for simple harmonic motion. But as I said, you're given that in the formula sheet, so don't worry about remembering that one because it is a little bit complicated, really. Okay, so that's that there. So the first one I'm going to apply it to is a spring idea. Now, again, Unit 2 physics dictates Hooke's law is equal to T equals K times delta L, and we should know T is equal to F, so F is equal to K times delta L. Okay, so that's Hooke's law. It's just another way of writing Hooke's law, and we can input this into that equation here. Sorry, you don't really need to draw this, but this is just to memorise what Hooke's thingy was about. Hooke's law, so that's some kind of mass there. And we can input that into that equation there. So if we input F equals K times delta L, K times delta L is equal to mg. Rearrange to get whatever you want. So if we wanted to get delta K on its own, K equals mg over delta L. Okay, so that's what that one would look like. If we wanted to input this A, we could change that to K times delta L equals ma. So rearrange to get A on its own. So A would equal K times delta L over m, and then substitute our idea of the acceleration is minus 2 pi frequency squared times the displacement into A. So that's minus 2 pi frequency squared times x equals K times delta L over the mass. Okay, so that's basically just adding together a few laws that we should already know. Basically, what we've done there is we've just used. The reason I've not gone through this is because it is really sort of Unit 2 AS Physics. Again, so is that bit up there. The only addition we've made is we've put our acceleration of a simple harmonic system, which is minus 2 pi frequency squared times x, which is x being a displacement, into that equation. Obviously rearranged it if we needed to, such as we've done over here to get A on its own, which we obviously put as the acceleration of the simple harmonic system, which, just to reiterate that, if I went through it a bit too quickly the first time, is minus 2 pi frequency squared times x, and x being the displacement. Okay, so as I said, we've just simply used a derivation of Hooke's law and rearrange it to get A, and then put A as our simple harmonic motion acceleration equation. But that's not the only one we can, well, that's not the only application we can use this for. So, what's another application? Well, go back to our good old friend, the pendulum. So I need to check, As I said, I'll leave them two rules up there. Right, one sec. Where is it? Okay. Sorry, there's a pendulum idea for that next. I just need to make sure I get the right idea. Okay, so imagine we've got a pendulum. Here, this is the base of it. And then we've got, obviously, there's the height of the pendulum, and that's the pendulum there, that ball on the end of the string. And it's oscillating sort of in like that direction. If we enlarge that bit, so if we enlarge it over here, per se, and we just focus on the stringy bit, to sound really bad, then it's going this way, and the weight is obviously acting downwards, but it's not acting straight down, so this is the mg here, and if we try to resolve this angle, we try to resolve this force here, so sort of directly down from, so it's sort of directly down from the pendulum, we would use mg cos theta. And if we wanted to do it in the direction of where it's going, so sort of a straight, so that's 90 degrees sort of thing from there to there, we'd use mg cos theta. And obviously the t up here, so that's the original thing, the stand. So it's not really extended anymore, just put the thing on. We're just using our standard trigonometry skills here. So obviously t is equal to mg cos theta, so we don't need to worry about that. And the only force, assuming there's no air resistant forces, the resultant force F is equal to mg cos theta. So it's sort of like, sorry, that's mg sin theta. Good ones, you spotted that one. So F is equal to mg sin theta. And as F equals ma, and we said A was equal to minus 2 pi frequency squared, obviously that's all that squared, times x. We substitute x into this equation here, so mg sin theta is equal to m times, now we're not going to put a, we'll substitute that value into there, so it's times minus 2 pi frequency squared times x being a displacement. Rearrange this, to get Oh, actually, you don't need to put that. Sorry, you don't need to put the acceleration thing in there. You can do, but you don't have to. Sorry, it's not going very good, this video. So mg sine theta equals ma. If you divide both sides by m, you cancel the m's out. So g sine theta equals a. And then now we can put in our a value of minus 2 pi frequency squared. So g sine theta equals minus 2 pi frequency squared, or a, whichever, times x. That equals a as well. For those of you that got a bit confused there. So that's the main part of simple harmonic motion covered, really. There's much more to that. Yeah, so hopefully you get that. All we've done there is used our mg sine theta and put it in our A equation into that. So again, this is Unit 2 physics. So the last things we've just done, just to reiterate them, is we've done our spring idea, and we've used the F equals K times delta L, and used F equals MA, mg, rearrange that and put our A value in, to get A on its own. A equals that. And then we've done the pendulum theorem, and we've just simply simplified it down into resolve the forces. And then we put F equals mg sine theta, and as F equals ma, we've put ma equals mg sine theta, so a equals g sine theta. And then we could put our a value into g sine theta equals a, so g sine theta equals minus 2 pi frequency squared times x being a displacement. That's what we've essentially done. Now there is one more thing that I need to share with you before we finish this topic. Now, what I'm going to do is I'm going to rub this little section out here because I want to leave this on there. There's a sort of a final wish of reminder that you've managed to survive this long, to be honest. I mean, I'm starting to lose the will to live and I'm the one teaching, so I don't know how you're feeling. Okay, so let's get rid of that. Let's corner this bit off the board here. Now, what we've done so far is, just to recap, because I do feel I'm going a little bit quickly, actually, just, I'm slowly dying, by the way, so there won't be too many more of these videos. Oh, some good life in there. So as I said, what we've done is we talked about simple harmonic motion, 2 principles, which are always on the top of the board, which I said were the acceleration is proportional to the displacement, and the acceleration is always in the opposite direction to the direction of motion. Then we talked about free oscillations, and we said free oscillations were oscillations of constant amplitude and there's no outside forces acting on them. And then we said that is actually related to something called resonance and forced oscillations. Forced oscillations and resonance being the opposite of each other. Forced oscillations being where the frequency of a system, so the pendulum, me swinging that pendulum, remember me saying I push the pendulum and I can alter the frequency. Then we said that the resonance occurs when it's the opposite of the forced oscillations, where there's a constant frequency, and where the resonance occurs where the frequency is equal to the natural frequency of the system. And we said the natural frequency of the system was where the it just vibrates at a vibrates, it oscillates at a constant frequency where there's no outside forces acting on it. And then we talked about the pendulum, and we talked about the spring, and we just related our F equals ma into both of the equations, or F equals mg into both of the equations, in terms of what we learned in Unit 2 physics. And then for the pendulum, we just did a force diagram essentially. Simplified it down to A, put our A value in as minus 2 pi frequency squared times x being the displacement, which, again, don't worry about that because that's in your formula book for A2 physics, so don't have to worry about that one. Then we're just going to talk about something called damping. Now, we've just talked about the oscillations, and we've assumed there's absolutely nothing that we can do. But the spring, if you think about the spring, to constellate in your mind why we're talking about this thing called damping. Now, if you think about the spring, springs are in many different things. The main application of springs, in terms of what we're going to look at in terms of damping, is used in cars. Now, for those of you that have used to play Colin McRae Rally, when you went on your testing for your car to get something called dampers, which is obviously going to relate to this, you had to drive your rally car over these hills and get your dampers as hot as they could be so you can upgrade them. Now, obviously, that's not going to get you an A2 physics mark. What is going to get you an A2 physics mark is understanding that in them vibrations, so when the car's bouncing up and down, it's having simple harmonic motions. It's not having anything else. I know what you're thinking. So, to reduce these simple harmonic motions, what the rally mechanics would often set something up is to be called critical damping. Now, that is something we can work with. Now, critical damping, what I'm going to draw is I'm going to draw a scale here. So, in the middle of this scale, I'm going to put critical damping. And I'll explain why I put that in the middle. Critical damping. Now, what is the aim of critical damping? Now, you might want to write this down because I'm not going to have no space to. Critical damping occurs where the force of the restorative force of critical damping. Basically, critical damping is where the oscillations are reduced to the equilibrium in the shortest time possible, obviously the rest of the equilibrium. So, what we mean by that is obviously when the rally car is bouncing up and down during these oscillations, if it's at critical damping, it will stop bouncing up and down as quickly as possible, and the rally driver can continue to crash and burn and get to the finish line backwards in a giant fireball. Obviously, none of that would ever happen, but just a bit of humour there. So, critical damping is where the vibrations stop as quickly as possible, and vibrations we mean simple harmonic motions, the bouncing of the car and the dampers in the car. So, that obviously, when we were talking about the simple harmonic motion of a pendulum, if we try and, so this is the equilibrium here, and it's going constantly past the equilibrium. And if we are at critical damping, it will pretty much stop like that. Now, that's because we are pushing, so when it goes up this way, so when it goes up that way, we're pushing it that way with the correct force just to stop it in its tracks. Now, there's two variations. So basically, you can think of this as restorative force. That's why I've drawn a scale on there. So, if we push too hard on this force, then we'd actually engage a higher speed. Sorry, people can't shut my door. We'd actually engage a higher speed going this way. Okay, I know we try and push it towards the centre, but then we continue pushing it towards the centre. We push it too far the other side, so we continue to oscillate. Oh, it's not a very good oscillation. So, too heavier force is something called heavy damping. Too lighter force, so this is the opposite end of the scale. Now, this is why I've drawn a scale, where we try to restore that. We use a small restorative force because obviously we know having a too big a restorative force causes it to speed up. But if we don't slow it down, if we don't do the opposite force enough, then we have something called light damping, where it still goes on for a very long time because we've not got a big enough restorative force. So this is light damping. So this is a weak force, and this is a strong restorative force. Okay, so that's sort of the main bit of damping. You don't really need to know much more than that. But as I said, hopefully that's been some kind of help. And just to recap on what we've done so far, we talked about the two factors of simple harmonic motion, free oscillation motion, resonance and forced oscillations, then we talked about the spring and the pendulum, and then we've gone on to look at damping and what we mean by damping. But apart from that, that's really simple harmonic motion. There is something else called energy displacement graphs, which I'm not going to go into too much detail about. Basically, it just looks like, I'm just going to show you the graph, just looks like that. See, I designed that, by the way. Oh, there's some damping graphs there at the bottom. Again, if you're in my class, it's just a class book, so some damping graphs there, if you can make that out. Anything else interesting? The time period of a pendulum is the 2 pi times the square root of L over G. So it's just that one there. Provided the angle does not exceed 10 degrees. Again, that's sort of it really for simple harmonic motion. We've tried to cram all that into about half an hour. Hopefully you've been able to understand it, and we'll see you in the next video. Thanks for watching.